Okay, it's my great pleasure to introduce Greg Wilmot. Greg did his undergraduate in the physics department here at Adelaide Uni, and now he's doing a PhD here in the engineering department. And he's going to talk about Clifford algebra. Over to you, Greg.
Thank you. So this is a walk through, starting with mathematics, introducing geometry, and then an algebra, and then physics. And made possible by Clifford algebra. And I hope at the end you'll understand why Clifford algebra is called the geometric algebra. It extends differential geometry. It uses the same backbone of exterior algebra, and extends it by adding the metric, which gives the spin and pin groups. And that is then a powerful tool that allows you to analyze calibrations, which also come from differential geometry. And the maps to Cayley-Dickson algebras also come from differential geometry. So we start with the simplest geometry, which is the geometry of simplices. But before we do that, we'll do the maths, which is Pascal's triangle, which starts off with a sea of zeros, and then you get a 1. And then you use the recurrence relationship that every next line, next row, every element is the addition of the number above and the number above to the left. So these are all 1s because there's zeros over here. But then you get a 1 for the number of vertices for the zero simplex, a 2 for the number of vertices, and 1 edge for the 2 simplex, 3 and 3 and 1 face for the 2 simplex. The 2, it's called 2 because it's represented in 2 dimensions. In the 3, when you get to 4 vertices, you have 6 faces. No, sorry, when you get to 4 vertices, you have 6 edges and 4 faces, and you have 1 tetrahedron, which is this column here, the number of tetrahedrons. You'll notice that, and then the next level up, you can't draw it as a projection like this, but you can do a trick where you put an extra point in the middle, and it's a schematic of a 4-dimensional object represented in 2 dimensions. But you can see the fact that there's 5 tetrahedrons in here. Each face through to the center point is a tetrahedron, and the whole thing itself is a tetrahedron, and gives you the number 5 here. So every simplex at every level includes all the other simplexes in there inside. So the one on the right-hand side is the actual final result, and then all the number of sub-simplices are given by Pascal's triangle. And the recurrence relation of Pascal's triangle means every time you add a new row, you add the previous simplex plus a new simplex with the new line joined, with the new vertex joined by lines to every other vertex. So every time you're adding a vertex, you're you're connecting it to every previous vertex. It's the same recurrence relation. You can't really draw a perspective geometry of the 5 simplex, but the 6 simplex you can, as discovered by Fano in the 19th century. It's a projection of a cube through one of the points of the cube. It has very nice projective properties, whereby every line has 3 vertices, every line has 3 vertices, and every vertex has 3 lines, which is similar to the 2 simplex. Every point, every vertex has 2 lines, and every line has 2 vertices. Now we're going to skip straight through to the 14th simplex, which has 15 vertices. And this is also interesting because it's a projection of a 14-dimensional object into 3 dimensions. of space, the tetrahedron. And we have Fano planes on every side. And in fact, there's 15 Fano planes in here, which we will show, which we'll prove. Where is it there? There's 105 edges, 455 faces. If we go back to the sixth simplex, there's 7 vertices, 21 edges. Well, that's actually each line here. It's not an edge, but a projection of a face. So every line here is a face. So there's 7 lines. So there's 21 edges in total. You can count the 35 faces in here. So this is actually a projection of the sixth simplex. Of course, you have to count the ones with the triangles with the circle edges, and you have to include certain triangles within triangles to actually get to the 35, but you can see them all. In the 14th simplex, I'm not going to try and bother counting the 455 faces, but the 105 edges is 15 times the 7. Every plane here has 7 lines, and 7 times 15 gives you the number of edges. And so we have this, and the final projective geometry of these 14 simplex is that it's very hard to see, but if you take that black line there, it joins 3 faces, 3 Fano planes. The one on the back wall is a Fano plane touching this edge. The one on the bottom is a Fano plane touching that edge, and the one through the middle here. So we actually have every edge touches 3 Fano planes, in all 15 of them. So that's another equivalent perspective geometry to the Fano plane. So I call this the Fano volume, and we will study it extensively. So we now move on to the algebra. How do you turn these things into an algebra, the geometric algebra? Well, you first turn the vertices, you erase everything by 1 dimension. You turn the vertices into vectors. You turn the edges into areas or planes, and you turn the area here into a volume. And we use the notation. We then use the notation from differential geometry, where we label this thing a 1 form, and the edge a 2 form, and the area a 3 form, representing the volume of 3 space, E1, 2, 3. Then notice that this line edge doesn't just join the 2 points, the 2 vertices or vectors. It actually translates you from one to the other. So you have to use a directed line. So we have a directed simplices now, and it has a parity. It changes in this direction. So E1 times E12 gives you E2, and of course, if you did the line the other direction, you'd have E2 changing by E21 back to E1. That means you can directly infer the rule for Clifford algebra product, which is the 2 vectors contract or go to base elements, become the number 1 if they're the same, or become the 2 form from Grassmann algebra if they're different, if they're orthogonal. If they're basis vectors and it's an orthonormal basis, then that becomes a 2 form. And that's actually rotations in the rotation algebra. It's either going to rotate, it's either the identity, there's no rotation, or it's a 90-degree rotation. So all the simplices define a complete basis for every n-dimensional space with an n-1 simplex. And then the next step is we say we don't need just orthonormal bases. We can put vectors on for the vertices, and we find that the edge is then joined by AB, which is actually the full rotation group in terms of sines and coses, where the element here is a unit imaginary number. I don't like using the name imaginary because it doesn't commute. It's an operator that has negative square. We also have the nice property that the algebra in 3 dimensions has the volume form, the 3 form, changes from E1 into E3 and vice versa. It changes a 2 form into a 1 form. And that allows you to define a cross product where the E321 times any plane or 2 form gives you a 1 form. And we can do that with a left-hand screw rule because we actually include the parity in here. Now, the 3 form is actually imaginary. It commutes with everything and it has square minus 1. So this is like complex, this is analogous, isometric to isomorphic to complex numbers, but you couldn't use I to convert between these two because imaginary number I doesn't include the parity. You'd have to define explicitly parity elsewhere outside of the equation. Right, so the final step is to take these vectors and multiply lots of them together. And the way you do that is you put them into the Pfaffian. And the reason why you do that is because the Pfaffian has the same property, recurrence relation, as the simplices. Every time you add another vector, you have to connect it to every other vector. And you're connecting it by both the metric part, the dot product, and the orthogonal part, the Grassmann part. And then those 2 parts separate out into a Pfaffian for just the metric, a complete metric in this case, as distinguished from differential geometry, on top of the orthogonal space, the exterior Grassmann space. You then realize that this has a cofactor, this is dependent upon determinants, and the determinants have a cofactor expansion, but so do Pfaffian and have exactly the same cofactor expansion because they're related. And so you can divide you can put partition, you can do an associativity here any way you like and multiply Pfaffian expansions in any way you like. So we can divide it into pairs of Pfaffian expansions, which is actually just the full rotation in 2 dimensions. So we can have n divided by 2 Pfaffian rotations in 2 dimensions to define this product. And that defines the spin group if n is even. If n is odd, well, you just get n minus 1 divided by 2 rotations plus 1 vector on the end. And vectors in Clifford algebra do a reflection. So that's the pin group. And the spin group is a double covering of the special orthogonal group. And it's double because it's a conjugate rotation. You have to multiply any element with the rotation element on both sides. And that means if the rotation was negative, you'd get the same answer. And the same with the pin group. The pin group is a double covering of the orthogonal group, which includes reflections. Now, how many reflections do we have for any particular algebra that you choose? If we go back to the previous slide, we can see that in 7 dimensions, a 6 simplex, we have 21 edges. Well, that's the number of rotations. So that's the number of generalized Euler angles in this form in the spin group to do any generalized rotation in 7 dimensions. The final trick here is that all odd algebras in Clifford algebra, the pseudoscalar, which is the largest element, the element on the right-hand side representing the whole simplex of the Pascal's triangle, anti-commutes with every vector because it commutes with every vector because it anti-commutes with every vector once and commutes with itself. So the pseudo-scalar is a commuting element, and in certain algebras, it squares to -1, so it's an imaginary number. In 7 dimensions, it also squares to -1, and in 15 dimensions, it also squares to -1. So that means that these 3 simplices are very special. And we can use the perspective geometry that we looked at before to actually define subalgebras of the spin group. These particular algebras, the simplices, are special because they have commuting pseudoscalars that are also square to -1, so they're imaginary. And if you multiply any element by the pseudoscalar, that's called the dual. So you multiply this element, this vertex by this vertex, and you get the 2 form, and you take the dual of that, you get the 1 form on the other side. So that means the dual of this form, this 1 form, times the dual of this 1 form equals the dual of that 1 form. That's a closed subalgebra of the spin group and of Clifford algebra. But that's just this edge multiplied by this edge gives you that edge, or sorry, that edge times that edge gives you that edge. And that's quaternions. That's the definition of quaternions. You then multiply that by the complex number, the pseudoscalar, and you get the full pin group, which includes both the spin and the pin group. And that's the whole of Clifford algebra in 3 dimensions, and we've just seen that it's actually complex numbers times quaternions. So that represents a closed algebra in its own right. The phenoplane in 7 dimensions also has the dual is just times the pseudoscalar, and the dual and the pseudoscalar is an imaginary number. And if you take this 3 form formed by these 3 numbers multiplied together, multiplied by this 3 form, then this common point contracts and you get the expansion of just those 4 points, which is a 4 form. You take the dual of that and you get back the line through the middle. So that means the dual of this line times the dual of that line equals the dual of that line. And because every line, every point is connected with 3 other lines, that defines a closed algebra, subalgebra of the spin 7 group algebra. And it involves 7 4 forms because there's 7 lines here. And if you multiply that by pseudoscalar, you get the full pin group, which is, you have to include 1, and this gives you the complex number times another 7 elements, giving you 16 elements altogether in this full spin pin group. Very nice way of defining an algebra, and that's very geometric. So let's carry on to 15 dimensions. We found the perspective geometry of here was every line shares, or every edge in this case shares, no, every line shares 3 phenoplanes. So if we take this time this line, then this face multiplied by this face, the line cancels or contracts, and you end up with the 4 form on this side plus the 4 multiplied by the 4 form on the bottom edge, giving you an 8 form. The dual of that, of course, is the plane through the middle. So again, this defines a spin algebra subset of the 15 dimensions, which I'm calling sharp algebras, that has 15 8 forms. And if you multiply that by the plus the unit 1, if you multiply that by the pseudoscalar, which is a number with 15 dimensions, and then you and it is imaginary, then you get the full pin group, which is another set of 7 forms plus the 15 form itself, the pseudoscale. Cool. So that's the sharp algebras. And now to use them. I've divided the algebra into 3 parts. The 7 form on the bottom, which is the original 7-dimensional Fano plane, and 2 other parts, 7 O forms and 7 P forms. We will now prove that those exist and what their properties are. But first, before we do that, we have to look at Cayley-Dickson algebras, because Cayley-Dickson algebras map from Clifford algebras. So from geometric algebra, we have calibrations, which I'll skip through here very quickly. A calibration is an exact form where it over any manifold, the scalar product with any set is always less than 1. But when you actually multiply it with the contact set, because you not multiply it in Clifford algebra, the scalar product in differential geometry, you get the answer is 1. Its maximum is 1. It's 1 single point. That and the exactness means that you can define a flux form, and in this case, it's the flux through the cube. And that by Stokes's theorem, the flux through the cube or through the boundary of the cube, if the manifold's a cube, then that equals the change inside the cube. And we know that because of the property of the scalar being a maximum of 1, then the volume for the cube is the 3 form itself, because the product is 1 at some point. What does that mean for the spin group? Well, the spin group is actually a fixed point variant of a calibration. And the spin group, they're always quaternions, so the quaternions are calibrations. And multiplying the calibration by the quaternions keeps them invariant, whether you're dealing with the calibration itself or the dual of the calibration. The interesting property is in Clifford algebra that these calibrations, whether it's the dual or this, are invertible. Now, before we get on to which algebra we're going to deal with, we have to define what the terminology and the notation for all the algebras. And we're going to stick with 3 dimensions of Clifford algebra and octonions. We have to decide whether we're dealing with a positive definite signature, where the vectors were positive, or a negative signature where the vectors are negative. The quaternions are the same in both cases. But we also could have variations between these 2 algebras where we have a mixed signature and indefinite signature. But simplices in the notation, the derivation that I've given, we haven't decided which metric to actually, which we haven't color-coded the vertices. They're all one or the other. So we only have definite signature. Being an engineering physicist, I'm going to choose positive definite for the vectors. And that means that the pseudoscalar is imaginary, which is a perfect property for us. When we map that to octonions, we could also map it to octonions with positive signature, the split octonions. There's no the other mixtures of signatures are all isomorphic to this algebra, so you might as well use all positive ones. But we're not going to do that. We're going to use just the negative signatures where it's all imaginary, not imaginary numbers, all imaginary operators in the octonions. Now the maps between those 2 algebras is in quaternions. we can use the 3 form to denote the mapping E1, E2, E3 to O1, O2 and O13. Now I'm using a graded notation here for the octonions. So it's easy to see that that's an XOR operation as a quaternion. It's just the sign that you have to worry about. But the sign is given by the parity of the mapping, and you can change the order of these things. You might think it's just a change of order, but that's anti-isomorphic to this, so we have to call them anti-quaternions. For the octonions, we get the 7 form is a mapping from the 7 forms in octonion in Clifford algebra, 7 dimensions, to octonions. And you can then do the same with 15 dimensions, mapping a 15-dimensional Clifford space into the Sidonians, where we have a 4th generator. There's 2 things to note here. One is the ordering of Grassmannian spaces are given by a natural ordering of the Grassmannian space. 1 forms are smaller than 2 forms, 3 forms or 4 forms. We don't use that ordering, but that ordering is very important for Cayley-Dixon algebras, but it's not ordered in the same way. It's ordered by the binomial theorem of the Pascal's triangle. So O12 comes before O3. And then the doubling gives you all the O3 elements, and then doubling gives you all the O4 elements. The other important thing to notice is that these can be interpreted as a map from quaternions inside the Clifford algebra space to quaternions in the Cayley-Dixon space. This is a map of 7 quaternions into the 7 quaternions here, but we've got 21 quaternions, or faces of the 6 simplex in this case. But we've chosen, because of the calibration, we've chosen ones that only touch each other once. So we're completely independent to define the parity of the faces of the simplex when we do this mapping. And that's very important. Here we've got 35 quaternions that map over to this space, which we will come to. So starting with the full analysis of the calibration for 7 dimensions, here's the calibration. Notice that the middle term's negative because when you map that to Cayley-Dixon, that would be an anti-quaternion. So under the mapping that we defined above, so we should put in a minus sign there to turn it into a quaternion. So we have 7 quaternions. And that's a definition then of octonions, where this index set 1, 2, 3 defines a product table for every element, because every pair of elements every rotation is defined once uniquely by this calibration. The dual, the 4 form with 7 terms, is actually very important. It's not really a member of the spin group, but each element is a member of the spin group and the sharp group algebra. And if we look at this one element, then we can see that it actually could be interpreted as a 180-degree rotation, or a part of a 2 pairs of rotations of 90 degrees. E1, 2, E3, 4 in this case, plus E1, 4, E2, 7, and E1, 7, E2, 4. And you define these as the pair of 90-degree rotations as alpha and beta, where alpha is the commuting part and beta is the 2 non-commuting parts. And what you find is this, and that's the full rotation, is defined by of the calibration, is the full rotation of the phi 7, gives you phi 7 dash. And what you find is you have this nice property of alphas and betas, where one's a projection operator, idempotent, and they're orthogonal. You find that the beta part, that just the 2 90-degree rotation part, actually has the full effect of the rotation all by itself, and the alpha part stabilizes that rotation. And furthermore, if if you choose the alpha betas correctly, well, if you choose the betas from this subset of 3 rotations for every of the 7 elements, if you choose the sign correctly, then it's a member of G2, and G is phi 7 dash equals phi 7. So the calibrations is invariant, and so both calibrations are invariant. So this algebra of G2 is automorphisms of Sidonians and automorphisms of the spin-sharp algebra. Right, we can go further with this notation of 7. We can see that the 7 factorial covers all possible variants here. There's actually 30 different calibrations which satisfy the property of being a cross product. Each one has 7 terms and 3 rotations, and there's 8 sign differences. But the sign differences come down to just a parity of plus or minus for every quaternion. But if you have a look at all those different sign combinations, there's 128 different possibilities for every of the 30 calibrations. 16 of them are octonian for every representation. But what about all the others, 128, or the other 4,000 possibilities? They're all isomorphic to one of these algebras, PK, K being 4, 8, 10, 12, 14, 16. And that number there is derived by the amount of non-associativity in the algebra. Well, that's really strange. There's supposed to be only 7 quaternions, and all the rest are supposed to be non-associative, such as in octonians. That should be 28 non-associativity. In fact, P28 would be octonians, but there's no paraassociativity. And what we found, I've called this P because there is paraassociativity. Each one of these has 12 zero divisors. And we would now need to analyze what the properties where the other non-associativity is. And it comes down to the ordering of the algebra. When you take the ordering into account, this is what we normally measure when we measure the associativity. If it's non-zero, then we call it non-associative in this column here. But if you change the order, you find you can get non-associative. So let's go back. The octonians are type X. It doesn't matter what the order is, it's anti-associative, alternate associative, and so they're all zeros. But if you swap the order of the others, then they can go from non-associative to associative, depending upon the order of the terms. And you can prove that there's only 3 cases, one of these being 0, and the other 2 being non-zero in all cases. So that's your 4 non-associativity types. When you take that into account, what you're finding out is when you count the P4 case that we came across up above, it's all B types. All 28 non-associatives are B types. And the other cases include more of the A's and C's symmetrically. So we find, using that analysis, that Cayley-Dixon algebras include 7 lots of P4s in U1, 12 times factor to 12, 7 lots of P12s in U2 and 7 lots of P4s, 14s in U3, and 8 octonians in here. So that's your 15 in Sidonians. I'm calling them U1 because when you get to U2, trigintoduionians are too hard to say. U3 does not have a consistent name. If U4, you would have to only call 128 onions, which is an impossible search term in your browser. So Kalgas proved in 2004 that there's 15 subalgebras, rings, non-associative rings or loops in Sidonians, 8 of them being quaternion, and he found that the other 4 were this algebra P4, which he called quasi-octonians. I'm calling all of this series quasi-octonians because they come in more, and because there's 12 zero divisors times 3 times there's 7 of them in here, that is why there's 84 zero divisors in U1, and every algebra after that has a factor of 84. increasing in 84 zero divisors. I call them U's because I'm calling them ultra complex numbers, as opposed to the complex numbers or the hyper complex numbers. The ones that have parasociativity are completely different to the hyper complex numbers and need a different name. So that's another story, the zero divisors, which I'm not going to go into. What I want to look at is the calibration for 15 dimensions. And as I said, it's got 35 quaternions in this form, where the middle term is negative, which is analogous to the 7-dimensional case to turn this from an antiquaternion into a quaternion. But that is not invertible, and the dual of it is a 12 form, which doesn't define nice rotations. If you analyze the Sidonian, the 15 subalgebras of Sidonians, you find a calibration in this form, where the A part is the base 7-dimensional Fano plane, E1, 2, 3, 4, 5, 6, 7. The O part is all the other planes that include 8. So they all have an 8 in them, so they all touch this vertex at the top. And the P plane is all the other planes, which don't include 8. So where are they? Well, of course, the one on the bottom is an octonion by definition. The one on the face here is octonion because it touches the 8. And if I multiply that by this form, I get rid of the 8 and all the other high elements, and that lowers it down to this middle plane in the middle here. So there's 3 of those from each side, giving you the 3 middle planes that touch the 3 edges. Where's the other planes? Oh, well, where's the 4th O plane? Sorry, the 7th O plane. It's the circle at the bottom touching the top wall, the top vertex, going through ACE on the edges. So it's a cone through the middle of here, and it touches everything 3 times, every face 3 times. And the dual of that, no, let's go with the other ones through it for the octonions. Every octonion touches every one through the middle here at the bottom face. Line through the middle also has a triangle that touches the Fano plane, which touches the 8. So that's another 3. So that gives you your 6 octonions, and the cone in the middle gives you your 7th octonion. If you lower the one through the middle by multiplying it by this factor, you get rid of the 8 and you get rid of the A and the B and the F in the middle, and you replace it with the C and the E, and you get these 3 circle ones here plus the cone through to this vertex here. And there's 3 cones through the middle starting from the 3 walls. So that's the P Fano planes are the ones that are cut through the middle diagonally, and the 3 cones that cut through from the outside walls, start from the outside walls as a circle. And the final one is the cone through the middle, taking away the 8 and the ACE, you get 9BD and the circle in the middle plus the point in the middle. And that turns out to be this thorn-shaped object. And the quaternions are the original one at the bottom, plus the faces, plus each side of that thorn is a quaternion plus the 3 lines. So that's your 7 faces. And if you flatten that out, you'll see a projection of the Fano plane. And the cone itself is shown here, and the 3 quaternions, the quaternion at the bottom, the 3 lines plus the 3 quaternions that are rings, go through to points on the other side of the cone. And that flattened out also gives you a Fano plane. So that's your 15 Fano planes of the Sidonians. And where's the physics in all this? Said I'd get to physics. Well, theory has had some success applying octonions to particle physics. And you can understand that because we saw that G2 was derived from the dual to octonions. And SU3 is a subset of G2. That's an SU3 is important for particle physics. Gresnet has more recently suggested the three colors could be accommodated in three octonions that are shared with a single quaternion, which we've seen many times. But if we go back to the Sidonians above, the Fano volume, you'll see that most of those are p-planes, p-Fano planes, and you couldn't have a family of particles with two octonions and one Fano plane with zero divisors. So you've got to find three octonions that don't have any Fano planes, p Fano planes, and that means you have to find three shared elements that all start at the top. And I'm going to suggest this line being the shared quaternion, and the three lines along the bottom. So that's the back wall, the front wall, and the middle wall through the A to A8. And that means the coloring would change as you go from one, as a quark rotates from one dimension to two dimensions, if these were found in a solution with these three being positive algebras in the, say, the split quaternions, split Sidonians, then it would change color as it goes from 1 to 2 in that orbit, but another quark would change from 2 to 3 in that orbit, and another one from 1 to 3 in that orbit, or some mixture of the lot. But we can do better than three colors. Remember I said that there was three lots of algebras in U3. This is U1. U2 is a projective geometry where three of these, and there's 31 of these inside U2, and they all share every three of them have a common Fano plane. They all share one Fano plane. And then the next level up is U3, which is so that would be a four-dimensional hyperfano volume. The next level up is a five-dimensional hyperfano volume, which every four-dimensional Fano volume is shared three times with one Fano volume, giving you another perspective geometry in five-dimensional space. And that's the geometry of U3, that fifth-dimensional Fano volume. And so you could imagine finding out of all of that 63 four-dimensional Fano volumes, one type for P4, one type P12, and one type P14, which gives you three generations of particles with different properties, which just have enough structure to be able to pull out leptons and three-color fermions for every family. And because of the different properties, they would have different masses, hopefully. That's the conjecture. And that's where we'll leave the physics, and we now come back to mathematics if I've got enough time.
Go for it.
Thank you. The mathematics is really hard, and that's why I've left it to last, and it doesn't actually make sense. So it needs some more work, or we change our definition of the mathematics. Automorphisms normally form a group, a closed algebra, and G2 is elements like E12 times E plus E47, 21 of them, and we can look at the spin group for the sharp algebra in 15 dimensions, and we find we have 28 rotations for every of the 15 terms. That's divided into three cyclic, three mixed, and four sign variations. The three cyclic, you have G2 at the bottom and a higher dimensional G2 at the top, and whatever sign change you use for that one, you do the same thing with the top one and corresponding indices. And so you get a reflection of G2 at the top. And surprise, you get a 15, no surprise, you get a 15-dimensional definition of G2. But you can do that for the 15 terms, and you can also have 4 mixed ones for 15 terms and 4 sign variations. The mixed ones swap between the upper and lower half, and the sign variations are on top of that 7. So that gives you 420 invariants of the capital Phi calibration, not the 15-dimensional one, not the 15 element 3-form one, but the Phi with 15 terms, 7 for 7-form. So we've divided it up into O and P parts. So let's look at what the O part multiplied together, and this we can multiply the O part, the A part automorphisms, and we denote the signs as upper indices 1 and 2. We're looking at both the cyclic and the mixed parts together. So there's 7 terms for every sign variation, and you multiply them together, and you get this interesting table, which actually simplifies into a change of basis into the 1, 2, 3 sign part, which is all of that part, and the 4 part. And so it's actually just the algebra of the 3 sign variations and the algebra of the 4th sign variation multiplied by Z2. So it's not very interesting. We'll come back to look at all combinations of this with multiplying by other things, but you can see it immediately, more complicated sign combinations. You can see immediately that the only time A multiplied by anything gives you a result, it gives you a mixed part of both the O and the P part. So if you multiply any A part by any mixed part, you get a mixed O or mixed P, you get this combination of algebras. Any other combination is not in this table, so it's a star, which means doesn't have 4 terms. It's not an automorphism, so it's not a closed algebra. That's interesting. So do we choose this part? Let's look at the other combinations where we multiply the squaring of the algebras of the parts. We look at the O part, we square that under a Lie product for the different sign variations. We get this structure where, surprise, surprise, the first one is the 15-dimensional G2, and that forms a doubling of it if you take the second sign variation, which is just the second 2 terms being negated. So that means we could have the automorphisms just being this part or just being that part. So we could have an S1 times G2 or an S2 times G2. If we take the whole lot together, it's not an algebra of G2 times anything, because this doesn't match G4 or the dihedral group or the 4 or the Klein 4 group, because it doesn't have the identity. Further complications, if you multiply any of the mixed ones together with between O and P, or O with O, then nothing is closed. You don't get any isomorphisms, any invariants of a capital Phi calibration. The P part itself, cyclic, looks like it starts off very nicely, but if you go to 4 times 3, you get non-invariance of the algebra. So you have to choose just this part. So what we've got is that the invariance of the algebra, the cyclic part and the mixed part for all of the A's, just the cyclic part and the cyclic part for just the cyclic part for the O part, and just the 2 sign variations for the P part. But we can't mix them together. We have to choose one if you want a proper automorphism subgroup as algebra. That's a complication. This is should be a subalgebra of sharp algebra. It's a subalgebra of a spin group algebra. It's a classical algebra. These should be all closed. So something's going wrong here. Maybe it's not a classical algebra because the matrix representation of these sharp algebras limits as the 90-degree rotations. As you go towards 90-degree rotations, that actually are isomorphic to identity. So it can't be represented in matrices, this algebra. So maybe we don't expect it to be closed. And all of these three parts are actually orthomorphisms with three domains. But at the moment, I'm going to put my bet on this algebra here in this full form. So it's not G2 times anything, it's G2 more complicated representation with a G2 15-dimensional subalgebra. I told you it was complicated. But we can now apply that. I've just applied that to the sharp algebra, but we can map this into Sidonians. But in Sidonians, we have an extra constraint. We need to have the 35 quaternions, the calibration with 35 quaternions being invariant as well. If you take that into account, then everything is not an invariant. It changes the representation for any other sign variation of the octonal cyclic or the p cyclic or the a cyclic mixed. They all change representations of S. And in fact, the p mixed ones actually change you to quasi-Sidonians. And G2 doesn't do that. G2 keeps it the same. This is swapping between the P's and the O's. P's and the O's, yes, which is not a good idea, I don't think. So for the automorphism of Sidonians, Schaefer proved that it's isomorphic to G2, and other people after that, following Brown, have said that it's G2 times S3. Well, it can't be S3, as I've shown. It could be S2, but that's not the full story. But if we look at the full explanation when we actually do the the full rotation in 15 dimensions, divided as a conjugate rotation divided into terms that commute and terms that don't commute with the algebra, then you get a similar algebra where B is the full rotation. B is the four terms, the four 90-degree rotation terms, the two forms, and it has the action of the full rotation group. And alpha is a stabilizer for that rotation group, but only for the G2 representation. So I'm betting that Schaefer is right, and that's the automorphisms of Sidonians. It's just the 15-dimensional G2 representation. Right. So what we've done is we've used Clifford algebra, bring calibrations from differential geometry into and the mapping to Cayley-Dickson algebras, and we've used the spin group to analyze them in a standard mathematical form framework. On the way, we've found the invertible Clifford group is more than just the spin and pin groups, but also calibrations. And I'm going to speculate that calibrations are the full invertible group. You can define all the spin and pin groups as calibrations. And Clifford algebras have calibrations for all of the symmetric group, including the monster. So the monster is 200,000 dimensions large, but multiplying 200 edges, 200,000 vertices or vectors by 200, which are single numbers in Clifford algebra, by 200, a bit more than that number of edges, so 500,000 Clifford numbers together is a lot easier than trying to multiply 200,000 sporadic matrices, sparse matrices. And so therefore we might be able to do better analysis for all of the symmetric group. And the other open question is, should we expect automorphisms of Sidonians to be connected? It's power-associative. This is a new area of mathematics that we need to investigate further. I thank my supervisors and thank you for listening.